And welcome to Postbag number 20. First package of the day, it says commercial sample IC module. And it is 2 samples. Will it focus? It's an SI5351 25 megahertz module. So clock 0, clock 1, clock 2. Now, is it going to work? We'll throw up the datasheet in a minute. Here we have the datasheet for the SI5351. Most of the boards you get off of AliExpress have got this one, the smaller chip. And as you can see, 8 kilohertz, 260 megahertz. Not going to use the full range. It's I2C driven. They tend to use a 25 meg crystal, and the core voltages are normally set at 3.3 volts. I say the most common package is this one, and because it's the cheapest chip and it gives you 3 usable outputs. Right, there's the small chip. As you can see, it has an I2C interface on 2 pins. It has 2 pins for a crystal oscillator. It has 2 phase lock loops, A and B, and the phase lock loops are used to take the 25 megahertz and multiply it up to a set frequency. There is a mux here, and so you can select what oscillator goes to what multi-synth. Basically, the multi-synths are dividers and the PLL is a multiplier. So to get the frequency you want out, you have to multiply your 25 megahertz up to a specific frequency, and then using the fractional multi-synth division, you bring that down to the output that you want. And so you do have issues that if you're using PLLA on 2 inputs, they're kind of linked to the output of the PLLA, and then the second one or the third one you can use from B. So however you use this, there is an issue with that PLLA or PLLB are driving this multiplexer, and so the relationship of the output frequency to one of these is the selection point in the mux and the division ratio in here. And so you can have issues that you can't really have a very high frequency here and a very low frequency here if both of these are driven from the same PLL. So there is a compromise you need to make. It must get worse when you use the ones with more outputs. So that's basically how this chip works. The crystal, as we can see here, there is a crystal input. The small chip only has the option for the crystal input, but it does allow you to select the load capacitance of sort of 6 puff, 8 puff or 10 puff on the input depending on your crystal, and you can program that internally on the registers. So it does save you do not need the external capacitors, which saves on real estate. That's a quick look at the block diagram, and as you can see, the more comprehensive chips have more outputs. They have a digital clock in, and they have a voltage controlled oscillator, whereas obviously the smaller chip, these functions are grounded on the inside and these outputs and things aren't used. I doubt if they change the chip depending on the body, they just don't root the bits out. So that's about it. It has I2C as it says, and there's a little bit down here. It can do high speed, low speed, and it has the set address, and it needs pull-ups. And another item for postbag. Is that in focus? 8 megabyte PsRam. An Arduino audio shield for a Tensy 4.0. And a Tensy 4.1. Pinouts. So that's going to be for an upcoming project. Well, this is just a quick look at the Tensy website, which is the PJRC store. And as you can see, there's the board. It's got the same processor as the Tensy 4, but it's running at 600 megs a clock. And we can look down and see what it's got. It's got pins for Ethernet. It can be a USB host. It has a micro SD socket, 35 PW pins, 18 analog, 8 serial, and it has 8 mega flash memory. And of course, you can also add an extra 8 megs of PRAM, which is why I bought the PRAM chip. It's breadboard friendly, but I don't care because I don't use breadboards. And it has some extra signals taken out for bits underneath that you can get to. So a total of 55 I/O pins, and then you get a picture of the actual I/O pins, what they are, where they are on the board. I bought it because I want to use it for audio. This is just a quick look at the audio shield. As you can see, it's just a small board that plugs onto the underneath and contains an SD card, and that is the serial I2S sound chip. And as you can see, there are line inputs, line outputs. There is a headphone socket, and there is pins to connect to microphone. You see, you can do. There's basically the pins for the pinouts on it. This is all on the website. All what it needs to do. As you can see, it just filters the supply a bit. It's a SG-TL5000 chip. And the next one. I'll just remove the paper. And what have we here? Will you be able to guess what I should be making? An ADE-1 Plus, which is a balanced mixer. I need 2 for what I'm going to be doing, but I got 4. To buy from the manufacturer, you have to buy 20, and I do want to buy 20, but I could get 4 samples. So these are 4 samples. Not sure if it will focus in on them. Here we have the data sheet, the ADE-1 from mini circuits, and it's basically a frequency mixer, commonly known as a ring diode mixer, as the diodes form a ring or a full wave rectifier effectively. And as you can see, it's from 0.5 meg to 500 megs, and it's a little plastic package with a little diode die and 2 small transformers. And so if we scroll down, we can see the schematic here. See, there's the ring of diodes or the 4-wave bridge, and basically you have a signal coming in, you have an IF frequency coming in, and you have a signal going out, and what goes out will be the sum and difference between the IF frequency and the frequency coming in. The way I'm going to use it is the IF frequency coming in is going to be very, very, very close to the frequency coming in. So basically what's going to come out is audio frequencies. And so they will then get fed to the Tensy board to decode. So basically the circuit will have 2 of these with a IF clock that is 90 degrees out of phase to give me 2 signals, which will then, the Tensy will then decode into audio. That's the plan. And so, you know, kind of mini circuits to supply 4 of these for free as samples, and we'll just have to see how it goes. Just thought I'd do a quick microscope view of the balance mixer, and as you can see on the left and the right are the 2 little transformers, and the blob in the center is the diode ring substrate. So balanced mixers. It's a huge box. No good. I'll switch over to the microscope to look at this one. There you go. ADUM4160. Now these are USB isolators. I've got 2 samples as I want to try isolating some USB, and this seems like the way to go. So that's what they are. As you can see, this is the data sheet for the 5 kV USB digital isolator, and I think the most important parts are down here. It's recognized by UL, and they've given it a 5000 volt RMS test, and it's passed all that. And you can see, yeah, good speeds, typical USB voltage and currents. So this is going to make a very good digital isolator, so that for my 3D printers and that, which I've got different buses on this side to that side, I won't have to worry about disconnecting the power or anything like that, and any transients will be okay. And the other one is I have some radios that are driven by RS-232, and these are also driven by USB to serial converters, and of course the radios connect to aerials on the outside of the house, and what I don't really want is some sort of like static build up on the antenna or things like that getting back into my PC. So the idea is one of these will sit feeding the USB to the radio's RS232 converter. As you can see, these are very small chips, just over 2mm square. I got these as a tryout, but I think it won't be possible, because when you flip it over you'll see that the balls are incredibly tiny and there's a lot of them. So I don't think I'll be using this, which is a shame, as it is a 2 ADC 1 DAC low power codec with audio digital signal processing, and it looked interesting when I ordered it, well, as a sample, and I don't think I'll be using them, so they might just stay in the might be useful later box. As I won't be using this, I won't discuss a datasheet much, but as you can see, it has a bias generator for electret microphones. It has 2 inputs, so like left and right, going through the ADCs, and I2C or SPI control ports, and it has a single output. So it looked quite interesting. You know, there was lots of things that you could do with it, but I think this will just go into the parts, as at the moment it's too awkward to make a prototype board with it. Shame, but hey ho, it's what comes from not reading the data sheets properly when you're looking for something. If you want to see more, hit the subscribe button, click that bell, and I'll see you on the next one.